Welcome to our video on chromatography. Before we start and heading over to the spectrophotometer, we have to first get the fractions of the dye.
But what are we using to filter the dyes? We are using a microscale pipette column to separate the unknown dye into its components. This works due to the fact that the components have RF values different from one another, making it so one dye comes out before the other.
So the first beaker we have here is a 50 milliliter beaker that's going to be holding the waste. So all of the solvent that drains out that doesn't have any dye in it is going to go here. Then we're going to have a beaker that has the dye in it, the first dye that comes out. Then we're going to have a medium, whatever comes between an intermediary beaker that will hold a mixture of the two different dyes before it completely drains out to the last dye. And that's what the last beaker will be before we go to the spectrophotometer. Okay, so now we're gonna add the 2 drops of our unknown dye to the top, and yeah, I know I got it. Never mind. Now we're gonna add 2 drops of dye to the top. That felt wrong, but it's okay.
All right. So now the first dye.
Squeeze it. Just squeeze it, bro. Squeeze it. You can barely see that shit. Okay.
Okay, so we just finished the filtration process, and we have the fractions for each one of our bays here. Here was our waste. This was our first fraction. This was the intermediary fraction as it switched from dye to dye. And this was our last dye, the diluted that came out. Now, we took those dyes and we put them right here. The first one is just the solvent. It will act as the base for the spectrophotometer, or to zero it out. This is our first fraction, diluted with deionized water. This is the intermediary, diluted with deionized water. And this is the last fraction, diluted with deionized water. Now we're gonna go head over to spectrophotometer.
Alright, I'm now gonna zero the base out, which is glacial acid. Now we're gonna put our first fraction of dye into the spectrophotometer. No! We're gonna put the factor in the Now we're gonna put the fraction in the spectrophotometer. But first we have to wipe it.
Now we're gonna put the intermediary fraction into the spectrophotometer. Make sure to wipe down both sides before you put it in there.
Now we're gonna put fraction 3 in the spectrophotometer.
Based on the values we got from our scan, here, the peaks on the absorption wavelength graph corresponded to fluorescent and to blue blue.
Now, before we end this video, there are a couple things we need to discuss. Why did we scan across all wavelengths in spectroscopy? There are 2 main reasons. First, it helps us find the lambda max, which is the wavelength where a substance shows maximum absorbance. Measuring at the lambda max ensures that the most sensitive and accurate results. Now, for the second reason, it detects multiple absorbing components in a sample, each with its own lambda max, aiding in complex analysis. Now, for the second part of this discussion, we need to break down what is called the Beer-Lambert law. So here's more about what these variables mean. Absorbance is what we get using the spectrophotometer, showing how much light is absorbed. Molar absorptivity is a constant that tells us how strongly a substance absorbs light at a specific wavelength. Concentration is the concentration of the sample in moles over liters, determined from known standards about the substance. And path length is the distance light travels through the sample, which is usually 1 centimeter. Now, absorbance and concentration are directly proportional, meaning a higher concentration will give you a higher absorbance. We always zero the machine with a blank. The zeroing ensures absorbance readings are due to the sample alone and not any absorbance from any other material within the cuvee.